All right, let's dive into one of the coolest parts of chemistry, playing chemical detective. We're going to uncover the secret recipes that literally build everything around us. So you might want to grab your magnifying glass because our first case is about to get started. I mean, really think about it for a second. We're all taught that water is H2O, but how do we actually know that, right? Why isn't it H3O or maybe HO2? How on earth did chemists figure out the exact number of atoms in a compound? Well, that is the exact mystery we're cracking today. And here's our first case file. It's this pretty simple-looking white powder, magnesium oxide. You get it when you heat up a magnesium ribbon in the air. But what's its real recipe? What's its empirical formula? We're going to use some actual lab data to find out for sure. Okay, so before we can even start looking at the clues, we have to understand the number one most important rule of any chemical investigation. This law is the foundation. It's what makes all our calculations even possible. And this is it, the law of conservation of mass. It sounds fancy, but it's actually super simple and incredibly powerful. All it means is that in a chemical reaction, you can't just create atoms out of thin air, and you can't make them disappear. They just get rearranged. So the total mass you start with has to be the exact same total mass you end up with. No exceptions. Let's see this law in action, okay? Let's imagine we have exactly 28 grams of our first ingredient, calcium oxide. You got that number in your head? Good. Now let's add the second piece of the puzzle. So to that, we're adding 22 grams of carbon dioxide. That means we have 28 grams plus 22 grams going into our reaction. Now, if the law is true, what should our total mass be at the very end? And would you look at that? We get exactly 50 grams of our final product, calcium carbonate. See? 28 plus 22 is 50. Nothing was lost, nothing was gained. The law holds up. It's kind of like perfect chemical accounting. But here's where it gets tricky, right? This is a classic puzzle. Sometimes it looks like the mass changes. What about when a gas from the air joins in or a gas escapes? Does that mean the law is broken? No way. It just comes down to your setup. If you're in a closed system, like a totally sealed jar, the mass you measure will stay exactly the same. But in an open system, like a beaker, the mass you measure on the scale might seem to change if a gas comes in or leaves. But the law is never, ever broken. The mass is still all there. Some of it just turned into an invisible gas and floated away. Okay, so we've got our unbreakable law down. Now let's get to know our suspects, the atoms themselves. Because if we want to figure out a recipe, we first need to know how much each ingredient weighs. You know, since single atoms are way too tiny to put on a scale, chemists had to get clever. They came up with this thing called relative atomic mass, or R. Basically, they compare the mass of every atom to a standard, in this case, carbon-12. This gives every element its own unique mass number. You can think of it like its own chemical fingerprint. And here's why that's so useful. The R for magnesium is 24, and for carbon, it's 12. Now, that doesn't mean a magnesium atom weighs 24 grams or anything. It just means it's twice as heavy as a carbon atom. It's all relative, and that relationship is what's absolutely key. And this whole idea scales up perfectly. If you add up the relative atomic masses of all the atoms in a chemical formula, you get what's called the relative formula mass, or MR. This basically tells us the total relative weight of our entire chemical recipe. All right, detective, this is it. We have the unbreakable law. We have the atomic weights of our suspects. It is time to analyze the evidence we collected from the lab and finally crack the code for magnesium oxide. So, here is our evidence log. These are the raw measurements taken straight from the lab. We weighed the empty container, then we weighed it with the magnesium inside, and then we weighed it one last time after the reaction created magnesium oxide. Trust me, the secret is hiding in these numbers. So the first thing we've got to do is figure out the mass of just our key players. If you look at that first calculation, we can see that by subtracting the container's weight, we know we started with exactly 0.24 grams of magnesium. Then, did you notice how the mass went up after heating? That little jump of 0.16 grams, well, that's the mass of the oxygen from the air that joined the party. Now we just follow a simple 3-step process to decode all of this. For step 1, we just list our two elements, magnesium and oxygen, along with the mass we just calculated and their R fingerprint. Okay, now for step 2, this is where the magic happens. we divide the mass of each element by its R number. This basically turns the mass into a number we can use to compare the amount of atoms. And look at that. We get the same result for both, 0.01. And finally, for step 3, to get the simplest possible ratio, we just divide both of our answers by the smallest number we got, which in this case is 0.01 for both. And that leaves us with a ratio of
a perfect 1-to-1 ratio. That's it. That's the secret code we were looking for. This little number tells us the exact proportion of atoms in our mystery powder.
And there you have it. A 1-to-1 ratio means that for every single atom of magnesium, there is exactly 1 atom of oxygen. That ratio is the formula. The mystery is solved. The empirical formula for magnesium oxide is MgO. Case closed. So what's the big deal? Why bother with these detective skills? Well, it turns out that once you know how to find a chemical's formula, you unlock a whole new set of tools for understanding what stuff is actually made of. For example, have you ever wondered what percentage of a fertilizer is actually the useful nitrogen part? You can figure that out using percentage composition. Or let's say you need to know exactly how salty a saline solution is. You can find its concentration. These are really powerful, really practical tools. Yeah, these formulas let you make some pretty precise discoveries. You could find out that 13% of all the mass in ethanol comes just from its hydrogen atoms. Or you could calculate that if you dissolve 8 grams of something in 2 cubic decimeters of water, you get a solution with a concentration of exactly 4 grams per decimeters cubed. This is the kind of chemistry that gets used every single day. So just remember, what we've gone through today is way more than just something to memorize for a test. These are the real, fundamental tools that scientists use every single day to analyze new materials, create new medicines, and just understand how the universe works on the tiniest level. And now it is your turn. You've got the method, you've got the tools. Here's your next case, copper iodide. All the clues you need are right there on the screen. Just follow the exact same steps we went through, see if you can find its secret recipe. Good luck, detective.